So you will be given n balls of n different colors, and you will need to determine the number of ways you can arrange this number of balls in a row. So if we have three colors, red, green and blue, so if we fix the first color to be red, then we can arrange the remaining two balls in two ways, green blue or blue green. And if we then make the first ball of color green, then we can also arrange the remaining two balls in two ways, which is red blue or blue red. So similarly, if we fix the first color to be blue, then we can arrange the remaining balls in red green, then green red. So each time, notice that the number of arrangements when the first ball is of color red is 2, and if the first color is of green color, then the number is 2, and then if both of them are of blue color, then this arrangements are the number of arrangement is also 2. So always it doesn't matter the what is the first color, always the number of ways to arrange the remaining two balls is same. So if we okay this is just what I was trying to say. So notice that if I fix the first ball's color, then we go on to arrange the remaining n-1 balls, then we are actually then left with n-1 balls of n-1 different colors. So from a bigger problem of arranging n balls of n colors, we are arrived at a new problem of arranging n-1 balls of n-1 different colors. So this is the recursive subproblem. We know that recursive functions call itself. So recursive problems contain another smaller recursive subproblems. So now let's see how we actually calculate the value of the number of ways we can arrange these balls. So if fn is the number of ways to arrange n balls of n different colors, then let's call this color C1, C2, C3, Cn, and let fn-1 and Ci denote that if we fix the first color of the ball and let's call the first color Ci, then we have n-1 balls, remaining balls to arrange. So let's call the number of ways to arrange those balls fn-1 Ci. So Ci is the color we are choosing for the first ball, so this is going to change. So firstly we took this to be red, then green, then blue. So we are going to loop through Ci. So So previously you have seen that if f3 is the number of ways to arrange these three balls, then if we choose the first color to be red, then we can sort the remaining two balls in f2 red ways, and then if we choose the first color to be green, then the remaining two balls can be arranged in f2 green ways, then and so on. So as we have seen, if the first color is red, it takes two ways to sort the remaining balls. Even if the first color is green, still it takes two ways to sort the remaining two balls. It doesn't matter what is the first color, so we can actually omit these colors, right? So since all of these numbers are equal, we can call all of them f2. So if all of them are f2, there are three f2s because there are three different colors choice for the first ball: red, green, blue, right? So f2 is actually fn. So if we want to solve this for all values of n, we know that actually fn equals to fn-1 c1. Here c1 was red, fn-1 C2 was green, and then Fn minus 3, n minus 1 C3, and C3 was blue. So if we have more than these three colors, then we'll have 1 2 3 4 and up to n colors. So we will have n different colors. So since all of these values are equal, so all of them will be called Fn minus 1, and since there are n values, so Fn is actually n into Fn minus 1. So notice that the value of the nth f relies upon the value of the n minus 1th f. So this is the recursive definition of the number of ways we can arrange n balls of n different colors. And there is actually another different argument to solve this problem. So notice that so suppose we have n different colors, C1, C2, C3, C4, and so on up to Cn. So if we want to arrange these balls in n different places, so let's call these boxes the places. So we want to put balls in these boxes. So in the first box, how many choices do we have for the first ball? We can choose actually any ball to put here. We could have chosen C1 or C2 or C3. So there are n different choices. So let's say we took C1. So if we take C1 for the first box, for the second box we have n minus 1 different choices, because we don't have C1 anymore because this ball is right here. So the number of choices for us is n minus 1, and then if we want to choose the third ball, we cannot choose C1 or C2, so we have n minus 2 choices left. So we have n into n minus 1 into n minus 2 into n minus 3 into and so on up to the last ball. For the last box we have one ball remaining, so that is the number of choices is 1. So the total number of choices is n into n minus 1 into n minus 2 into n minus 3 till 1. So the total number of ways is this. So actually we have a name for this special product. This is actually the product of numbers from 1 to n. So this is actually called a factorial n. So factorial n is written as n and then an exclamation mark. So this is called factorial n, and factorial n means the product of all the natural numbers from 1 to n. So since this is the definition of n factorial, so n factorial starts from 1 and ends at n. So n minus 1 factorial should start at 1 and start at 1 and then end at n minus 1. So from 1 to n minus 1 we have is n minus 1 factorial. So we can write this as n factorial equals to n into this, and this is actually, we know that this is actually by definition n minus 1 factorial. So this is n factorial equals to n into n minus 1 factorial. So just like the previous recursion, fn equals to fn into fn minus 1. So notice that the definition of n factorial is dependent upon the definition of n minus 1 factorial. So here is the recursive definition, recursive subproblem. So if we want to really calculate the value of factorial, we can just easily write a recursive function. And notice that these are a lot of mathematics, but we don't actually need mathematics for data structures, but I'm just giving them here as an example so that you can learn how to find recursions in thinking. So all of these things we have done here so far has numerous examples of recursions, because arranging n minus balls is actually the same problem as arranging n balls, and fn equals to n into fn minus 1, which is another recursive definition for fn, and then we have n factorial equals to n into n minus 1 factorial, which is also a recursive definition for n factorial. So if we move on to code this, we just need to write the recursive definition in the else return clause. So n into effect n minus 1, and this is actually the base case, because uh, we need to arrive at a value of n where we make no more further recursive calls. So from n equals to 1 we return 1. So when n becomes 1 we start returning. So if we want to simulate this function, let's call this function with factorial 5. So factorial 5, since 5 is not 1, so this will go to the else case, and then it will call 5 into factorial 4. So factorial 4, since 4 is not 1, so this will go to else case as well. So this will call 4 into factorial 3, and then up until we go to factorial 1. So here the value of n has become 1, so this is the first time we have to return. So from here we will return 1, right? If n equals to 1, return 1. So factorial 1 will immediately return 1, and this has returned 1, then 1 and 2 will get multiplied, and then we will return 2 to the previous recursive call. So this has returned 2, then 3 and 2 will become 6 and will return to the previous recursive call. So 6 has returned 24, then 24 has returned, and 120, which will return to factorial 5. So factorial 5 is actually 120. So this is how we calculate factorials.